This is part 2, the final part of our introduction to spectroscopy. In part 1, you will learn the general things about the various wavelengths and what they can do. This now gets specific. First, in review of wavelength and wave number, the wavelength and frequency are associated by this equation. Frequency equals speed of light divided by wavelength. When you do these calculations, remember that the wavelength has to be in meters. Well, we've also defined the wave number, and the wave number is the reciprocal of the wavelength. It is proportional to the frequency and to the energy, so it's a very useful concept, wave number. Now let's talk about UV-VIS. The visible runs between 380 and 780 nanometers. The ultraviolet, higher energy, between 10 and 380 nanometers. Now below about 200 nanometers, the air is absorbing the ultraviolet light, and instruments must be operated under a vacuum. So the near UV, between 200 and 380, you can operate in air, but not below that. Now, how many micrometers is 780 nanometers? Take a moment to realize that nanometer is a smaller measure than the micrometer or micron. And I think you'll see it's 0.780 micrometers. In the UV and visible, recall that the best visible colors in water solution were seen in transition metal salts. What that means is that visible light specks are useful for determining the absorbance and concentration of transition metal salts, something we'll see when we study Beer-Lambert law using the transition metal salt, and I believe that would be copper sulfate most likely. Now we can look at molecular substances that don't absorb visible light, and therefore they don't appear colored to the human eye. The absorption of ultraviolet and visible light only takes place in molecules where the valence electrons need just a little energy to jump to the next level. And again, absorbance below 200 nanometers is not seen in the typical UV spectrum. So you can see that the bonding pi, antibonding pi transitions are going to have high molar absorptivities. Here are the UV wavelengths and the functional groups in organic molecules that they are associated with. So for instance, the double bond carbon, as in ethene, you're exciting from the pi to the antibonding pi, and you're doing that about 171 nanometers. The triple bond, which is a shorter and higher energy bond, is in hexine, is a pi to antibonding pi excitation at 180 nanometers. The carbonyl carbon bond, as in ethanol, is from, again, the normal to the excited, or antibonding pi, and then you've also got a pi to antibonding pi at 290 and 180. So when you have this, you're likely to see absorbances at these wavelengths. Then we have the nitrogen to oxygen double bond, as in nitromethane, similarly as we have up here, down here, 275 and 200 nanometers. And then when we have halides involved, carbon to a halide, as in methyl bromide or methyl iodide, we're going to see sigma transitions to a sigma antibonding, and 205 to 255 nanometers will be seen in your spectrophotometry. Organic molecules such as these do not absorb in the visible spectrum. That's why they're not colored, but they do in the UV. And so we can use the ultraviolet spectrophotometer to find concentration as we do with colored salts with the visible light spectrophotometers. Here's some other concepts important to UV-VIS. You can use it to some extent for compound identification, but you see these functional groups all over the place, so many compounds will have very similar spectra. And solvents can cause a shift in the absorbed wavelengths. So if you add ammonia to the copper 2+ solution, you may remember doing this, it got a whole lot more blue. So you have to use the same solvent when you're comparing absorbance spectra for identification purposes between two compounds. Many inorganic species are going to also absorb energy in UV-VIS, so again that complicates the identification. And in fact, UV is frequently used to measure concentration when we know what we're working with. Now we'll move to the infrared spectroscopy, and this is really exciting for helping us identify compounds. Absorption of electromagnetic energy in the infrared region causes changes in the vibrational energy. They're going to stretch at higher energy levels, typically 6,000 to 42,000 joules per mole, corresponding to wavelengths of 2.5 to 40 millimeters. Now we are in the longer wavelength, and therefore wave numbers of 250 to 4,000 reciprocal centimeters. Now, we're going to assign bands to the vibration of particular functional groups in molecules. So, for instance, if you have an alcoholic group, we're going to get absorption here between 3,000 and 4,000 reciprocal centimeters. And you're going to see similar things for the single bond between the carbon and hydrogen in an alkene. A little bit shorter wave number, lower wave number here is attributed to a carbon-hydrogen bond when you have three different functional groups attached to the carbon in a tetrahedral configuration. The triple bonded carbon to nitrogen and carbon to carbon absorbs here in the roughly 2300 wave number. Here's our carbonyl carbon, down a little lower wave number in the vicinity of 1700, and here's a carbon-to-carbon double bond that we see in things like benzene. That's again going to be a lower wave number. Here we have the carbon-to-oxygen single bond that we find, for instance, in things like esters. And your worksheet has tables showing you even more associations like this. The IR spectrum then can help you identify the various functional groups on organic molecules and distinguish between organic molecules. Each group is going to absorb energy at a fairly specific wave number. So for instance, from the prior slide, you can look at the carbonyl carbon and see it is absorbing at 17 to 1800 reciprocal centimeters. This example shows you how an organic chemist might think through the structural formula of a compound. And this is C5H10O. We have a molecular formula but not a structural formula. We would go through and find these various absorbance peaks and associate the wave numbers with the tables and see exactly what we have. For instance, between 3,400 and 3,200 reciprocal centimeters, you see there is nothing going on. So there's no OH or NH present. Around 3,100 reciprocal centimeters, there's no peak to suggest we have an unsaturated carbon-hydrogen bond. So there's nothing here. But at 2,900 reciprocal centimeters, it looks like we have a saturated carbon-hydrogen bond. At 2,200 reciprocal centimeters, there's nothing, so there's no unsymmetrical triple bonds. And at 1710, you have a strong absorbance associated with carbonyl C double bond O. 1610, there's no absorbance here to suggest a carbon-carbon double bond. And so this is the more likely structure. It's called 3-pentanone. Here's another example. Again, 3400 to 3200, nothing there. But a moderate peak here, suggesting some unsaturated carbon-hydrogen bonds. A weak peak at 2900 here, indicating a possible saturated carbon-hydrogen. No asymmetrical triple bonds, because this is empty of absorbance. A strong carbonyl absorbance at 1690. And at 1610, weak absorbance bands consistent with a carbon-carbon double bond. And so it looks like we might have this. And if we had the molecular structure, we might easily get the other structure, acetophenone. And you can take your turn here. Which of these three do you think this is? Use your chart and turn the projector off while you're doing it. There's your molecular formula. NMR spectroscopy, which we don't really get to do unless we have a very strong lab, flips nuclei. The nuclei have a spin, just like electrons, and they're assigned quantum numbers. If compounds with atoms, like these, are placed in a strong magnetic field, they absorb in the radio frequency at specific energies when they flip. We're looking here at 0.1 joules per mole. Now, remember, the IR energies are thousands, tens of thousands of times larger. The UV-VIS, 1,000,000 times larger. And so that's why we need strong magnets to do this. The nucleus spins and produces a magnetic moment or dipole along the axis. And the relative values determine the frequency at which energy can be absorbed. In proton magnetic resonance, the instrument is detecting the energy difference between a +1/2 or low energy spin and a -1/2 higher energy spin. So we apply electromagnetic radiation to excite the nucleus into the higher energy level, and the frequency at which that happens is going to tell us something about the structure. The NMR spectrum arises because nuclei in different parts of the molecule have different magnetic fields because of what's next to them. And this is an NMR for something with only one kind of hydrogen in it. This is going to have two kinds of hydrogens in it, and so you have two peaks. The bigger one is the CH of the methyl group. And ethanol is going to have three peaks. The methyls, this secondary carbon-hydrogen bond, and then the hydroxyl hydrogen. So you see three peaks, and there you go. They are proportional in size. Methyl, methylene, and hydroxyl hydrogen peak. Spin-spin coupling is just a matter of each one of the hydrogens is going to affect the others, and so you get these little minor lines showing up around the major lines.